Okay. So anytime a physical or a chemical change is made, there's some sort of energy process that's happening. Okay? Some energy is involved somewhat. Okay? In a physical or a chemical change. And I want you to start thinking about the difference between a chemical and a physical change and see if we can pinpoint some of those energy changes. I think the last thing we did last class was talked about different types of physical changes and different types of chemical changes. So can somebody give me an example of a physical change? Yeah, Evan, what do you think?
Like a smoothie, a mixture of it, blending things together.
Okay, that's close. We're going to talk about mixtures specifically today. But what about just the change of one single element?
Boiling water.
Yeah, boiling, freezing, melting, those are all changes of state. Those are all physical changes. And then anytime we just change the look of an element, like we grind it or we mash it up or something like that, that's a physical change. Okay? So let's talk about physical changes and the energy that goes into them. If I'm going from a gas to a liquid, is the temperature getting hotter or colder? Gas to a liquid, we're getting colder, right? So are we adding energy or are we removing energy? Or removing energy, right? So if we're going from a liquid to a solid, are we adding or removing energy? If we're going from a liquid to a solid, we're removing energy, right? Particles are slowing down, it's getting colder, okay? That's a removal of energy. If I go from a solid to a liquid, what am I doing? Adding or removing energy? We're adding, right? We're heating it up, we're making those particles move faster, we're breaking bonds between atoms. That's what causes it to go from a solid to a liquid. Okay, does that kind of make sense? Do we understand the energy process behind that now? Okay, then in a chemical change, give me some examples of chemical changes that we talked about last time. Yeah?
Baking a cake.
Baking a cake, good. Right, we start with ingredients and we end up with one final product. Yeah? Burning, okay. Burning is a good example. What type of energy is given off when something burns? What type of energy? When something burns, like, is it warm or cold? Warm, right? It gives off heat. Right? That's a type of energy transformation. What else does it give off when something's on fire? What else does it produce? Smoke, yeah, but is it dark or light?
Dark.
Light.
Fire?
I mean, like the substance is getting.
No, it emits light, right? It lets off heat and it emits light. So those are two energy transformations that happen when something burns, right? In a chemical change, we can see heat and light energy both being emitted there. So the types of energy that we'll really look at are heat, light, and electricity. That's the third type. We didn't really talk about electricity much, and we don't talk about electricity much in chemistry, but heat and light are both good indicators that a chemical change has taken place. Any questions so far? Okay, energy in and of itself is never created or destroyed. Never created or destroyed. And that phrase right there is a pretty famous scientific law. Does anyone know what that law is called? Okay, that energy is never created or destroyed. Does that at least sound familiar a little bit? Okay, do you remember the name of that scientific law? Okay, this is called the law of conservation of energy. Okay, and you might have heard conservation of mass or matter. But this is the law of the conservation of energy. So if something is conserved, that means that it's neither made or taken away, right? Created or destroyed means it's not coming from nowhere and it's not disappearing. Right? It's only going to change forms. So an example from a light bulb. If I turn on my light bulb, what's the immediate energy that we see? Light, right? It immediately emits light energy. If it burns for too long, what do we start seeing? Or what do we start feeling? Heat, right? It'll transform itself into heat energy. That energy will be absorbed into the system, and then when we turn off that electrical outlet, the light bulb, whatever, we'll see that energy start to transform back to the system. So energy is never just created from nowhere, destroyed from nowhere. It's taken from somewhere else and then made into something new. Okay, now we're going to talk about mixtures, which we started to get to last class. We talked about physical and chemical changes, but it's a whole different type of matter. A mixture is a whole different ball game here. So here's the definition or what a mixture really is. Okay, a blend of two or more types, each retaining its own properties and identities. Okay, so we can mix two things together, but we're not making a new substance. Okay, because if we mix two things together and we produced a new substance altogether, what would that be considered? Sorry, I'll say it one more time. If we were going to combine two things to make something brand new with its own identity, what would that be considered? A chemical change, right? That would be a chemical change. So these are mixtures. And there's two main types of mixtures. I don't know if we've heard these words before, but there's two main types of mixtures that we're going to talk about. Okay. The important thing for us to remember about a mixture is that most of the time, mixtures can be separated again. Okay, so once we make them, we can separate them back out. Unlike in a chemical change, those things are hard to separate. So I want you to start thinking about some types of mixtures that we see in everyday life, and then we'll try to put them into one of these two categories. Okay, last thing we need to know about a mixture is that its composition, okay, or what's another word for composition? Yeah, what it's made of, right? Its makeup, it has to be identified. It has to be given to us. So in a chemical setting, mixtures have to be identified, what's in this thing, right? If it just looks like clear liquid, we don't know, is it water? Is it acid? Is it base? Is it salt water? We don't know. So a mixture has to be stated in its composition. So an example of how we would say that is we'd say this is a saltwater mixture that's 95% water and 5% salt. Okay, that's just an example. You don't necessarily have to have that down in your notes. That's just an example of what we would look at with a mixture and how we would write that. Okay, so the first type of mixture that we're going to talk about is something called a homogeneous mixture. Okay, a homogeneous mixture. And what a homogeneous mixture means is that it is the same throughout. It's uniform in its composition. So what does it mean for objects to be uniform?
Same amount.
Yeah, it means the same, right? So for something to be considered uniform, that means everything is the same, okay? So if we have a mixture that is uniform in composition, that means the entire sample of solution should look the same, all the way through it, all the way up, all the way down, nothing sticking out, no chunks of anything, things aren't falling to the bottom of a solution. It's the same throughout. Okay, so that's what a homogeneous mixture is known to be. Okay, it's also called a solution. So if we hear the word solution, that means it's the same throughout, and it's also called a homogeneous mixture. Okay. This second bullet here, same proportions, that's kind of restating what we said before. The entire thing is the same throughout. Okay, there's the same amount of salt to this amount of water throughout the whole thing. Okay, so if we have one type of mixture that's the same throughout, our next type of mixture is called a heterogeneous mixture. So what do you think that probably is going to mean? That's right, it's not the same throughout. So it's not uniform in composition. It's not the same everywhere you look at it. Okay, and then in general, right, this last bullet applies to both types of mixtures, okay, so it's not just heterogeneous mixtures. In general, mixtures can be separated using lab techniques, okay, and these lab techniques, for example, are filtration, so if we filter something out, using a centrifuge, or if we evaporate something off. Okay, so I'll let you write these down, then we'll talk about those techniques here. We talked about water not being a mixture because it was pure. And that's what we're going to talk about here, is a pure substance. Boys, thank you. A pure substance has what we consider a fixed composition. Okay? It never changes, whether we look at a tiny sample of it or a huge sample of it. A pure substance has a complete fixed composition. Okay, so when we talk about mixtures, we talked about we have to label the composition, right? Is it 95% water and 5% salt or whatever? Not all salt water is the same, right? That's why salt water is not a pure substance. Just like all orange juice isn't the same. That's not a pure substance. Okay, all Kool-Aid's not the same. It's not a pure substance. But if I look at pure water, right, or pure carbon dioxide or pure sodium, things like that, those should be 100% that element or that compound, with no impurities, no nothing. Okay? So this is how a pure substance is different from a mixture. Okay? It differs from a mixture by these points. Every sample of a pure substance has exactly the same characteristic properties. Okay? Or just properties. You can put properties. Every little sample I take of pure water should have 2 hydrogens and 1 oxygen. 2 hydrogens, 1 oxygen. Nothing else. No minerals, no fluoride, no nothing. If it does have those things, it's not considered a pure substance anymore. Okay? These properties can be used to identify that substance. Okay, so some properties of water that we know, we like to use water as our pure substance example because it's the easiest and it's the most common. Okay, so let's think about a couple things that we know about water that can help us identify it. Okay, and just think here for a second. Okay, so pure water has its own properties, right? It's a pure substance, it's a fixed compound, and it's got specific properties. What are some things that we know about water that could help us identify it? If there's two things of clear liquid sitting next to each other in a lab and you have to identify what they are, how do we go about doing that if we know one of them's water and one of them's not? What are some tests that we could do to help us identify which one's water?
Seeing at what temperature it freezes and what temperature it boils.
Perfect. Great example. We try to find out what temperature they freeze at and what temperature they boil at, because we know those things about water, right? We know that it boils at 100 Celsius and it freezes at 0 Celsius. I thought I was making it backwards. But we know if there's a jar, the other jar is acid, right? It might not boil at that same temperature. So we have each pure substance has its own properties that allow us to help identify that substance. Yeah.
It was like pure water, like water bottle water.
Mm-hmm.
Not pure water is like out of your sink.
Yeah, and even water bottle water, you know, like might not be 100% pure. There might still be minerals in it or whatever. But pure water is like, yeah, lab, like until it's cleansed and filtered and clarified and removed of all impurities. A lab setting could strip it all the way down. But yes, essentially bottled water would be pure water. Yeah. Does that make sense? Mm-hmm. Okay. As pure as, you know, drinking water requires. Whatever the FDA says is pure. All right, properties of a mixture depend on relative amounts of mixture components. So in a mixture, not in a pure substance, in a mixture, we depend on how much is salt and how much is water, or how much is peanuts and how much is raisins and trail mix and M&Ms and stuff like that. That gives us the composition. But water is always H2O, no matter what. Okay, so mixtures don't have set compositions, properties. Pure substances do. Be both water. Pure substances can be both compounds like water or elements like sodium, calcium, magnesium, any element on the periodic table. So either one of those can be considered pure substances. Okay, water is a pure compound and sodium is a pure element. But any element could go here, right? Oxygen, nitrogen, whatever. Okay, those could all be pure elements. This guy you might have heard of, okay? I'll talk about him in a second. So by the 1800s, the middle of the 1800s, only 60 elements had been discovered. Only 60, okay? And how many elements do you see on your periodic table today? 118. 118. Here. These guys go fit up here. Okay. 118. So less than half, they are just under half, almost half, were discovered in the 1800s. Okay. So at that point, this guy named Dmitri Mendeleev, he developed an organizational system for the elements. Okay. Have you heard the name Mendeleev before? Maybe. Hopefully you've heard it. Maybe not. Okay, but that's okay. You might want to be familiar with it. Tuck it away a little bit. He developed this organizational system for how to organize these elements. Okay, because there were 60 of them. He thought by this point we need to kind of get them organized a little bit. Okay? So he was the first one to really put an organizational system in place for the elements. Okay, he listed his elements in columns, and he listed them by their atomic mass. Okay, so he listed them by atomic mass, and then he grouped them next to similar elements. Okay, so he put them into columns, and then he grouped them by similar elements. So let's look on your periodic table real quick. Can somebody tell me what's the atomic mass of beryllium? Look for beryllium. Tell me which one is the atomic mass. Beryllium's in the top left of your periodic table. What's the atomic mass, Madeline? Perfect. Okay, so on your periodic table, here's the element. Here's beryllium. There's a number up in the corner. 9.012. Okay. This right here is the atomic mass. And this is the atomic number. Okay, and let's talk about the difference between those two things really quickly before we move on. Okay, does anyone know the difference between those two numbers? All right, let's talk about atomic number first. That's this one up in the corner. Atomic number tells us the amount of protons in that element. Is that ringing a bell? Yeah. Okay, good. The atomic number is the number of protons within that element. Okay, so every beryllium atom has 4 protons. If we find an atom that has only 3 protons, what element is it? It's lithium, right? It's no longer beryllium. So if we change the number of protons, we change the element completely. We can change electrons all we want. We can change neutrons all we want. We can't change protons. Okay? Otherwise, we change the element. So the atomic mass, then, is the number of protons and what? And neutrons. That's right. Protons plus neutrons equals the atomic mass. Okay, so that's how Mendeleev arranged his periodic table, by the number of protons plus neutrons, known as the atomic mass. Okay, understood? All right, good. Here's Mendeleev's table in columns, and then he grouped them by what he thought was similar acting elements or similar behaving elements. Okay, so he put it into columns. Does this look anything like the periodic table we have over there? not so much, right? So look at this one, and take a look at your periodic table. We see beryllium, then below it we have boron, below it we have carbon, below it we have nitrogen, oxygen, fluorine, and then sodium. Do these elements fit together on the periodic table anywhere? They go across. Right now we're lined up across instead of in columns, and we'll explain why here in a little bit. Okay, so he got the grouping part of it right, or he had an idea for the grouping part of it, but we adjusted it a little bit. Okay, this guy was so smart, and he left gaps in the table of where he thought elements should fit in. Right? These elements had not been discovered yet, but he thought, based on the patterns he saw in these elements, that there should be something that fits here, so I'm going to leave a blank for it. Right? That's a pretty smart dude. Okay, so he was advanced enough to understand, like, there's elements out there we haven't found yet, and I think this is where they're going to fit, because this is what they behave, this is what the atomic mass should be. Here it is. Okay. He even predicted the new elements, what they were going to look like, act like, what they were going to weigh. Right? Where did he think they were going to fit in on the periodic table? He predicted that stuff. And those elements went on to be discovered and fit exactly where he thought they should. Okay, so he's a smart dude. Okay, so this was Mendeleev. He arranged his periodic table by what? Okay, columns, but by what of the element? What property of the element? Atomic mass. Okay, he was the first one, and he did atomic mass. Mendeleev. Okay, tuck that away. The first guy to set it in the table in the order of atomic number, which it is today, was a guy by the name of Henry Moseley. Okay, he set it in the order of atomic number, which is how it's laid out right now. Okay, so if you look at your periodic table, you'll start to see them increasing in atomic number as you go across and then as you go down. It allowed these element characteristics to repeat at more regular intervals. Okay, and it allowed us to show that these elements really do act similarly, and these elements really do act similarly. So rather than just kind of grouping them together like Mendeleev did, he put them in order of atomic number, and then laid them out so that we could see really repetitive patterns about characteristics. Into groups and periods, okay, otherwise known as columns and rows. Have we heard that before? Mm-hmm. Groups and periods? Okay, good. So we're going to talk about groups first. Groups are the columns. They go up and down. Up and down. Okay, and on your periodic table, those group numbers are labeled for you. Okay, so I want you to see that up at top of each group. It says 1, and then it even says 1A. Okay, you don't need to worry about the 1A or B part, but I do want you to look how it says 1 through 18 all the way across the periodic table. Okay, what I would like for you to do is either highlight those numbers or circle them or rewrite them even, so that you can start identifying where's group 17. Where's group 18? Where's group 13? All that kind of stuff. You can identify that across. So you can highlight them if you want or rewrite them. However you want to do it is fine. But I want you to label the groups on this periodic table. Up in the very top right here, there's a 1. Right, this is group 1. And this is group 2. So just highlight the 1 and the 2 so you can start recognizing that hydrogen is group 1. Right? Beryllium is group 2. Oxygen is group 16. Yeah, so all those numbers. You can rewrite them, or you can just highlight them or circle them or whatever works for you. But I want you to start knowing what those group numbers are. Okay? And when I was taught the periodic table in high school, when I learned it, count how many groups are in this transition metal part right here. Count how many groups are right there in that little chunk in the middle. How many are there? Sometimes your book calls them families, and I won't ever do that, but your book does sometimes, so I want you to understand that those are the same things. Those two words are interchangeable, but I'll always call them groups. Okay, groups are based on similar chemical properties. So within a group, within a column, those elements act similarly. Okay, so as you go down through a group, so let's look at group 15. What does group 15 start with? Nitrogen. So nitrogen, phosphorus, arsenic, antimony, and bismuth. Those are the 5 elements in group 15. They have similar properties, okay? They kind of act the same. They've got the same number of valence electrons for the most part. They act pretty similar. The same goes with group 18, right? What's in group 18? What element starts group 18? Helium, right? Helium, neon, argon, krypton, xenon, radon, the noble gases. Those guys all act and behave extremely similarly, okay? So it's not going across that we see patterns. It's up and down. Okay. Now let's look at the horizontal rows, which are called periods. Okay, so groups go up and down, periods go across. And for your periodic table, you will have to label periods. So if you want to label these out to the side, hydrogen and helium is period 1, starting with lithium is period 2, 3, 4, 5, 6, 7. Stop at francium. Okay, we'll talk about what those 2 little extra guys are down at the bottom. But you might have to label those. They're not, I don't think they're labeled for you. So there should be 7 periods. Stop at francium. Okay, so what do you notice as you go from left to right in a period? What do you notice an increase in? Atomic number and atomic mass. Yeah, we see both of those increases, right? And we know the periodic table here is organized by what? Atomic number. This periodic table is the one we use every day now is increasing atomic number. It also happens to increase atomic mass as we go, but it's meant to be organized by atomic number. So as we go across, we see an increase of atomic number. When we get to the end, we jump down. Okay. All right. As you go from left to right on the periodic table, our properties change. Chemical properties change. Okay. So going from lithium to beryllium to boron, carbon, all the way to neon, lithium and neon do not act the same. They don't look the same. They don't act the same. Okay. So that's something really important for us to remember. As we move across a period, we don't have similar chemical properties. As we go up and down in a group, we do. But as we go horizontally, we don't. Okay, so lithium and neon act nothing alike. But lithium and cesium act a whole lot alike. Okay, does that make sense? Okay. All right, elements that are close together on the periodic table tend to act similar. Okay, they tend to act more alike, especially if they're in a column. But typically, if they're close together in the periodic table, they have some similar properties or characteristics. Okay. For this next part, we're going to talk about metals, metalloids, and nonmetals. So I want you to open up the back of your textbook because it does a good job of color coding for you what group on the periodic table is metals and what's metalloids and what's nonmetals. Okay? So we're going to talk about each of these groups, but you might just use that as a guide for you in the periodic table I gave you to kind of help you through that. Okay, so let's talk about metals. I'm going to list a lot of characteristics of metal for you, and I'll give you a few minutes to write them down, and then we'll talk through what they mean. Okay, so I'll give you a couple minutes to write down these characteristics of metals in general, and then I will talk about what they mean. Okay? So metals are typically shiny, right? The opposite of shiny as a characteristic is dull. Okay, so most metals are shiny. They're good conductors of heat and electricity. So what does it mean to be able to conduct heat or electricity? One more time.
Like produce heat.
Close. Yeah.
It travels from using.
Yeah, it travels through them. So yeah, it does produce it on the other end, but it's got to start from somewhere. So it'll travel through them well. Okay, so metals allow heat and electricity to travel through them really well. Okay, are solid at room temp. What's the one exception to that? Do you remember? Does anyone know the exception? Yeah. Mercury. Mercury is the exception. It's the metal at room temperature. A liquid at room temperature. If you look on that periodic table up there, the two blue elements, bromine and mercury, those are both liquid at room temperature. Those are the only two elements that are liquid at room temperature. Very rare. Okay. All right. The next characteristic is something called malleable. Do you know what it means to be malleable? Yeah, you can bend it, you can shape it, and most importantly, you can pound it into a sheet. So what would be metals that are good examples of being malleable? Alumina, tin, right? Those are things that you can pound it into a sheet, make a can out of it or whatever, things like that. Okay, that's what malleable means. So you can write that down if you need to, right? Pound it out or maneuver it. And then the last one is ductile. Have you heard that word before? Maybe a new one. Okay, in order to be ductile means you can draw it into a wire. You can roll it out or pull it out into a wire, a really thin wire. So what would be an example of a metal that is really ductile? You couldn't say it.
Copper.
Yeah, copper. Copper would be an example of one that's really ductile. And there's lots of other ones that will. Most metals can be done, drawn into a wire. Last, they have high tensile strength. So what that means is that when we hit it with a hammer, it's not going to shatter. Okay? It might like get a dent, or it might not even show anything, but it's not going to shatter. Okay? So the opposite of high tensile strength means it's really brittle. Okay, so okay, then here's just a couple of different properties. Mercury is a liquid. We talked about that. Those are the main examples of characteristics of metals. So if on a quiz I ask you, name 3 characteristics of metals, right? You got to give me 3 of those. Okay? Or 3 characteristics of metals that you know outside of these. Okay? But it's got to be a characteristic of a metal. Okay. Last, I'm going to just talk about some examples here that are different. Some metals, like in group 1, the group 1 metals, lithium, sodium, potassium, those guys, those are really soft metals, and you can cut them like with a butter knife almost. Okay, they're really, really soft. Most are not like that, but some of them are. So those are some pretty soft metals. Some of them are really tough, like chromium, tungsten, titanium. Those are really tough metals. Iron, those are things that are kind of on the opposite end of the spectrum. Okay, so you can see there. All right, here's some examples of like a soft metal here. It's being kind of just cut or shaved with a knife. Okay, real soft. There's a really shiny, shiny metal. There's a metal that's being manipulated to a wire, which is called ductile. Good, we're pulling it out to a wire. And then there's some more examples of a little bit more of a brittle metal. Okay, most are pretty strong, but that's a little bit more of a brittle. Do you see how it's kind of broken into pieces like that? Okay. All right, now I want to make one more point with metals, because I didn't make this yet. In your textbook, metals are red and blue. So what part of the periodic table are most metals found on? The middle and the purples and the pinks are metals also. So the whole left side is metals, okay? If you want to make that stair step, see that red stair step line on the periodic table up there? Or in your book, between the orange? Okay, you can make that stair step on your blank periodic table, so you know this is kind of from left over here is metals. Non-metals now are going to be on the complete right side of the periodic table. Okay, so on your book, those are the browns and the greens. Those are the non-metals, okay? Most non-metals are gases at room temperature. So in your book, there are the browns and the greens, and then the gases at room temperature on this board are the red elements. Okay, all the ones up on that periodic table that are red are gases at room temperature. Okay? In your book, those are the browns and fluorine and chlorine. These are the ones that are gases: oxygen, nitrogen, fluorine, chlorine, plus all of the noble gases. Okay, those are gas at room temperature. So the 4 there in the corner, and then all the noble gases, which is group 18. Okay, some nonmetals, however, are still solid at room temperature. Okay, and those are things like sulfur, carbon, phosphorus, and iodine. Okay, those 4 are nonmetals, but they're still solid at room temperature. Since they're nonmetal solids, they're really brittle. Okay, they're easy to break. Okay. Bromine is the lone nonmetal over there that we haven't covered. That's because it's liquid at room temperature. It's blue on that periodic table. Kind of sticks out. Okay? But bromine would be liquid at room temperature. So if we know that metals have specific properties, nonmetals are going to have pretty much opposite properties. Okay? Nonmetals are poor conductors of heat and electricity, which means they don't travel well through oxygen gas or xenon or chlorine or whatever it is. Okay, they're not going to travel well through that. Okay, then here's some pictures of nonmetals. Because I can't show you a picture of a gas. So. Last little section here is metalloids, and on your periodic table, those are the orange. Okay, so the metalloids surround that stair step. Okay, so that stair step that you drew on your periodic table, metalloids kind of surround that stair step on either side. Okay, metalloids are just what they sound. Okay, they're kind of metals, but kind of not. So their characteristics fall right in between metals and nonmetals. Okay, there's some of each. All of the metalloids happen to be solid at room temperature. Okay, so that lends itself a little bit more toward the metal side. They fall right in the middle in terms of how malleable they are or how brittle they are. They're less malleable than metals, but they're more brittle. I'm sorry, but not as brittle as the nonmetals. So again, they just fall right in between.